All right, a neat thing happens in our notation, and good notation helps us out. And so, if we look at PEMDAS, and we recognize that addition and subtraction were the same thing with an inverse, multiplication and division were the same thing with an inverse, and we're going to find out that exponents and roots are the same thing with an inverse. And what I mean is that I can write something as being squared, or to some power. Right now I'll talk about squared because we've worked with radicals. And so if I had n, if I had b squared is the same as b times b. And so I had a neat little rule that said if I had the square root of something times the square root of something, I got n back. And we're going to start watching some properties of powers going on here. And we're going to be able to expand this and use this for multiple things. What I'm going to do is I'm going to define any power here, and then we're going to circle back and look at what we can do with square roots. And then we're going to use this to kind of talk about our PEMDAS. So we're going to take a little journey in a circle here about patterns we see in numbers. So the first thing I'm going to do is I'm going to talk about how I define an exponent. And I'm going to say that it means I'm doing multiple multiplications, and I'm doing them n times. So whatever my base is, times, I multiply as many times as the power. So this is the base, and this is the power, or the exponent. And so if I do b, right, I have b n times, or b to the nth. So for example, 3 squared is equal to 3 times 3. I've taken my base and I've multiplied it twice. And we noticed this when we were doing factoring. In fact, I said, hey, there's a 1 hanging out in front. Well, let's build some rules from these. Then, if I take b to the m and I multiply it by b to the n, we're going to have bm times bn times. Right? I'm going to expand this out, b times b times b, and I'm going to do that m times. And then I'm going to go over here and I'm going to do the same thing, but these are all multiplications. And so all together, I have m plus n multiplications. And we say b to the m times b to the nth is the same as b to the m plus n. That's nice. Well, if I have b m times divided by bn times, then I'm going to write this out. M times. And I'm going to divide it by n times. Well, each one of these will cancel. And so I'm left with this one minus however many cancel here. And so b to the m divided by b to the nth is m minus n. But notice, since exponents are built on multiplications, and multiplications are built on additions, they're reflective of each other. If I look at what the power is doing, I'm multiplying powers. Multiplying powers, I add exponents. I look at the level below. Now, if I'm dividing exponents, I look at the level below. Well, here comes the neat parts. If I take b to the nth and I take it to the nth power, what does that look at like? Well, it's saying I'm taking b to the m and I'm multiplying that n times. Right? I just take the definition I used for an exponent, and I don't worry about this one being to the nth. I just worry about this whole thing in the parentheses. But look what happens. This is a whole bunch of product rules. B times b to the m is m plus m. B times m is m plus m plus m, which is the same as multiplying m by n. And so if I take an exponent to a power, I look down below and I do a multiplication. Exponent rules are kind of neat. The notation is kind of circles back on itself. Well, let's do a trick here. I said, hey, let's take the square root of b. Now, before I get the trick, anything to the 0 power is 1. And we talked about this back in factoring. And so there's a 1 hiding in front of these. And anything to the first power is itself. Right? We don't write the ones. So let's look at a pattern I can do here. If I take b to the third and I divide it by b to the first, that's the same as subtracting exponents, so I get b squared. And so I'll use this as 1. B to the third over b to the first, I subtract the exponents. I want to take this and I'm going to continue doing that. Come over here and I'll divide this, and so that's b to the first. Now if I take b to the first over b to the first, anything divided by itself is 1. That's the same as b to the 0. And that's why we know this is true. Right? When I first introduced it, I said, hey, we're factoring and there's always a 1 hiding in front. But now this pattern I create in exponents tells me, hey, that pattern's true. And one of the things we're going to see with mathematics is when we come up with new symbols, those new symbols are built on the patterns we've done before. But here comes the neat bit. I'm going to take b to the 0, and I'm going to divide it by b to the first. And that's going to give me b to the negative 1. But since b to the 0 is also 1, that's like 1 over b. Negative exponents flip things around the fraction bar. And so b to the negative first over b is equal to b to the negative 2, or 1 over b squared. And so there's a pattern that works with exponents. Let's use that pattern to make things, and make things useful for us. First thing I want to make is I want to get rid of square root signs. I hate them. They're a pain to write. We use them with other powers. Right? The cubed root of 8 is 2. And that's saying that 2 cubed is equal to 8. It's a way of reversing exponents. Well, if I put b in here, what I'm saying is there is some number times itself that's equal to b. So some number, some b times itself is equal to b. And so I'm going to put mysterious exponents in here. So I'm going to say, I don't know what these are, but it's going to be times itself. And b is 1. So some number times itself equal to b. I wrote that wrong here. I'll just write it like this for right now. If I say b square root of b times square root of b is equal to b, is what I wanted to say. Square root of b times square root of b is equal to b. And I'm going to say, well, there's some b to some power equals 1, because this is b to the first. Well, that's the same as bx plus x equals 1, or b to the 2x equals 1. Well, these have to be the same for this to work. And so that's like saying b, and so 2x equals 1, x equals 1/2, or b to the 1/2 squared equals b. Right? So multiplying anything by itself is squaring it. And so b to the 1/2 squared is b. Well, let's use our newfound power rule. That's the same as b times 2 to the 1/2 equals b, which that is b equals b. But that's the same as the definition of the square root. And so we can talk about roots as being fractional exponents. And so that means these rules that we built work for roots also. And that means rather nicely that exponents and roots are the same things of each other. In fact, they're inverses of each other. And so our patterns we've been using the whole time hold up for us. Well, what are the rules of exponents? Let's put them together. So any base to the 0th power is 1. Any base to the 1st power is itself. If I multiply exponents with the same base, I add exponents. If I divide exponents with the same base, I subtract exponents. If I take an exponent to a power, I multiply exponents. And I can write roots as fractional exponents. Well, that's a pretty powerful notation tool. We're not changing number, but we're letting our notation do work for us. And so let's look at a couple of these and how we can use those. I can take 3 to the 4th power and multiply it by 3 to the 2nd power. And that's the same as 3 to the 6th power. I can take 2 squared, and I can take the whole thing to the 4th power, and that's the same as 2 to the 8th power. Okay. Multiplying the same base, I add exponents. Taking a base and its exponent to a power, I multiply them. I can take 3 to the negative 2, and that's the same as 1 over 3 squared, or 1/9, right? And I can take the cube root of 8 and write that as 8 to the 1/2, and that's 2. And we'll explore roots in more detail as we go on, but we now have this powerful exponent tool. One of the first things people use this for is we decided to look at the number 10. Remember, we have a base 10 number system, and we wrote our numbers, right? That's the ones place. That's the tens place. We used exponents to do that, which also meant that we could write decimals, because that's the tenths place, that's the hundredths place, and that's the thousandths place, as negative exponents. 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. Well, scientists like to estimate how big something they're working with, and so they've invented a notation that exploits this, and it's called scientific notation. And it allows for multiplication and division of large numbers rather quickly. It doesn't help with addition and subtraction, but it helps with multiplication. And what it does is, if we take a number, 3.206 times 10 cubed, 10 to the third. What we're saying is 3,206. And we're multiplying it so that the first number, so 10 to some, so I want to say this first number is between 1 and less than 10. And so the numbers we write will always be some number between 1 and 10, not including 10. Can be 1, but it can't be 10, because because 10 can be written as 1.0 times 10 to the first. And then we express the power to represent the place value. And so 3,206 is 3.206 times 10 to the third. Now the power this has for scientists is the power this will have for science is that this represents how good the measurement was. And that happens with the number of significant digits. And this says how large the thing being measured is. So for example, the population of the Earth is estimated to be thousands, millions, billions, 7.5 billion. Well, in scientific notation, that's 7.5 times 10 to the ninth. Well, but tens and powers of tens talk about where the decimal place is. We go back to our base system of numbers. 10 to the 0 was the ones place. And so what we can do is we can look at the decimal point here. Right? This number has a decimal point. And if I move over 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places, I get my number between 1 and 10. And that's how we create scientific notation. Now, I can do the same thing for really small numbers. Right? This is a very small decimal. But if I move over 1, 2, 3, 4, 5, 6, 7, well, this is 4.18 times 10 to the negative 7. And so we kind of have two rules. We move the decimal point until our number is between 1 and 10. And if we moved it to the left, the number of places we've moved it to is positive. Okay, and so we get a positive 9. If I've moved it to the right, the number of places is negative. Now here comes the useful part of scientific notation. Let's say I have 7.5 times 10 to the ninth people in the world. And each of them ends up with, let's say, I know roughly for a fact that fingernails grow about 2 centimeters per year, or 2 centimeters per year, so that's 2/100ths of a meter. Right? And so if we take everyone's fingernails growing, I'll write this in scientific notation, 2.0 times 10 to the negative 2, I can tell you the length of all the fingernail growth in the world in 1 year. Take everyone's fingernail clippings, put them all together, and string them in a line. It'll be this long. Yeah, it's a weird thing to think of. The reason I remember this number is I just was talking to a geology class, and it's also about the same rate that England and the U.S. is moving apart due to the tectonic plate motion. And so I'm thinking of fingernail growth currently. But notice these are just multiplications. even though I'm writing my number in this specific way, I can move my multiplications because multiplications are commutative. And because they're commutative, I can write them in ways that are easier to calculate for me. And so now I have the same base times the same base, so I add exponents. So that's 10 to the 7th. And 2 times 7.5 is 15. Now this is bigger than 1. So I'm going to move my decimal place over 1. And that extra decimal place goes into my power. And so if I were to line up everyone's fingernail growth, I'd get 1.5 times 10 to the 8th meters of fingernail growth. It's actually quite a lot. That's a lot more than I thought it was. Sorry, I used an odd example. I just pulled that out of my head. I should probably stick with the book's examples. But powers of 10 is what helps us calculate quickly. And it's a thing that helps scientists organize and figure out how big of a problem they're working with. So let's see. I'm going to use the idea, the national debt problem. I should have went right to this. So in January of 2016, the national debt was $18.9 trillion. So let me get our national debt in 2016. 18.9 times 10 to the 12th dollars. Now if we divide that amongst each person, and what are we going to state that the number of people are? It's like 3.22, 322 million. And so there are 3.22 times 10 to the 8th people. And so this is the debt, and this is the number of people in the US. So let's divide the two to figure out how much we each owed or were part of the debt for. Now what's nice is scientific notation. I'm already seeing my powers of 10 line up. So I'm going to break my fraction apart and put this out front, and I'll put my powers over here. And so my power rule says the same base division I'm going to subtract. And so I have 10 to the 4th. Now my first part here, you know what? I'm going to guesstimate. I'm going to not be so exact on the calculator. I'm going to guess. And what I'm going to say is, well, that's close enough to 18, and that's close enough to 3. I'm going to round this one down and round this one. I'm going to round them both down because I'm doing a division. And that's about 6. And so 6 times 10 to the 4th, well, I'll convert it back. So to convert it back, I have to undo what I did. All right, so if I was moving to the left and that was 4 decimal places, well, to undo it, I'm going to have to move to the right. 1, 2, 3, 4. So that's 6 with 4 zeros, or $60,000 per U.S. citizen. Now the actual answer, if you plug it into a calculator or look at the example in the book, is 5.87 times 10 to the 4th, or $58,700. Right? So if we plug this initial thing into the calculator, we get this. I don't think my rounding trick is too bad. And that's really what scientific notation was invented for, was so that you could get in the ballpark. If you're designing an experiment, you really needed to know where the power of 10 was, and I'm close to 60,000. And I would say if I found a way of getting $60,000 to or from each person in the U.S. to cover that, the difference of that $1,300 isn't going to hurt. And so that's exponents, exponent rules, which we've touched on both in factoring and here in scientific notation. And we'll keep expanding our notations so that they can be more useful for us. All right, enjoy the module. If If you need anything, shout.